All right, welcome back everyone. I'm Mr. Keeney. If you're watching this, then we are about to go over our next section of notes with geometry. We just finished up our first section, which is a lot about vocabulary and our notation and how we can communicate certain terms. Today we're going to be talking about and building upon those components, I'll say, that we talked about this last section, and now introducing some maybe a little bit about distance, about values. So learning targets, I can use the vocabulary we use based on the undefined terms, which we had 3 undefined terms, point, line, and plane, to develop the foundations of geometry. I love how they said that. We're developing these foundations now. So we kind of got the words, the meanings, the descriptions, the definitions. Let's do something with it. The I can statement. By the end of this, I can add segment lengths using the segment addition postulate. And postulate, ooh, that's a scary word, but it's really not scary at all. So we're going to talk about 2 things to start off here. The terms, postulate and theorem. So these are pretty well related to each other, obviously different, and you're going to see them all year long. And there is a fundamental difference between the two. So terms, postulate. Postulate is a rule that is accepted without proof. So we just accept it. It is an assumption that we say, yes, we're assuming this is true. We're assuming it. A theorem is very different. A theorem is a rule that is proven. So we're able actually to take the things we know about geometry and say for certain this is true. We will see more examples of this, and we're going to be proving theorems ourselves later this year, and we're going to be introduced to postulates today as well. I do want to take a second to say postulates are a lot like our points, lines, and planes. Those are those undefined terms that we just, I don't want to say assume, but they're undefined. We know what they are, and we're not really challenging it. Same thing with postulate. We're assuming that to be true. This next section we're not going to do. If we were in person, I'd have you get your ruler out. We are online. You're watching the video. If you happen to have the physical copy, go ahead and get your ruler and measure those segments, and then come check with me later. But I want to go down straight to the ruler postulate. So this is an example. More than anything, this is just an example for you to see. Here is an assumption that we have in this model of geometry. It says the points on a line can be matched 1 to 1 with real numbers. The real number corresponds to a point is the coordinate of the point. This is something that we assume to be true. We do not need to prove that if we were like on the x-axis per se, and a point were on the value 3 on there, we don't need to prove that that's where it's at. And also what the ruler postulate says, go down here, the blank between points A and B, written as AB, is the absolute value of the difference of the coordinates A and B. So a lot to unpack, a lot of weirdly important. I say weirdly because it's just one sentence, but my goodness, it actually ends up being important for us. First of all, the distance, and you might have been able to guess that, the distance between points in AB, written as AB, is the absolute value, and that's actually a important one too, of the difference of coordinates A and B. So let me just give you an example of what they're talking about. Let's say down here, points A and B, let's say they're on the x-axis. So let's say x1 is really, it's at 4, I don't know. And this one is at 9. What they're saying is because we have coordinates, we should be able to find the distance. So to sub in down here, AB is equal to the absolute value of 9 minus 4, which would be 5. Absolute value, because if I were to switch this, let's just say we switched them up, and we looked at AB is equal to 4 minus 9, you'd see that we still get 5. So the reason is because we're dealing with geometry. We're dealing with distance here. We're dealing with positive lengths. If you were to drive here to Columbia, let's say it's about 100 miles from where you live. If you drive from Columbia back home, did you drive negative 100 miles? You did, and you still drive to 100 miles because distance is that absolute value. So we're not going in that negative space when we deal with distance. We are always going a positive amount. If I walk across the room, that's a positive amount of steps. If I walk back, that's a positive amount of steps. Another thing is this guy right here, AB. And I want to talk about, I'm going to change colors, that's how important it is to me, about the difference between this and this. So the first one, this one right here, we will read that as segment AB. It has the segment bar, its line segment, I guess you could say line segment AB, and its endpoints A and B. Now this guy right here is not going to be read as segment AB. So we read this one. Let me write down segment AB. And there's our little quotes. This one does not have the segment bar. We're not talking about the segment. Intuitively, we might know in our head, okay, this is a segment. We're finding the measurement, the length of the segment, but it's just that. We're finding its length, the value. If you see AB together, I want you to think this. The distance from A to B. And that is why we have the difference there. So when I want you to read this, I want you to think the distance from A to B. So in the case down here, what I'm looking at, we would say the distance from A to B is 5 units. I forgot my units. They didn't give us one. We'll always put units. So really key, important idea there. If it has the segment bar, we're talking about the segment itself as the whole. If we just see AB, we're thinking the distance from point A to point B. And that is how we will use the notation to measure it. So let's actually look at examples of that. And here comes our second postulate, the segment addition postulate. Now this will be something you will use quite a bit. And I want you to really take in with this next one about what it really tells us. It says if B is between A and C, then AB plus BC equals AC. If AB plus BC equals AC, then B is between A and C. Here's what it's saying. So I'm going to draw a picture. I love pictures. I think it's going to be, so I'm going to say, it says if B is between A and C, if B is between A and C, and it doesn't have to be in the middle, but I just happen to put it in the middle. AB, so that would be this part right here, plus BC would be equal to the whole entire thing. That's all it's saying. It's saying the parts will add up to equal the whole. The sum of the parts is equal to the whole. So with that in mind, we're going to use that in these next two, and we're going to specifically use this equation to help us with these next problems. So segment addition postulate, part plus part equal whole. The sum of the parts equal the whole. Let's go ahead, like I said, to take a look at examples. So examples, find RS. So we have this picture here. It has QR with 9. We have that missing value, RS, and then we have 22. I want us to use that equation. So the segment addition postulate, here is what it tells us. So based on what I know from this picture, I know that QR plus RS equals QS. That is what I'm able to say. I don't know much because we just started with geometry, but I know the segment addition postulate. Using that, I'm able to get that part QR, which is this piece right here, plus part RS equals the whole thing. Now the whole thing's highlighted, QS. And now what I'm going to do is I'm going to use a little bit of algebra properties here. I'm going to sub in values. So I have QR is 9, so QR is 9, plus I don't know what RS is. That's actually our missing value over here, so I'm going to leave it. There's nothing to substitute in. Is equal to, and then give me QS. QS is 22. From Algebra 1, probably from before Algebra 1, we know that if we have our equation here, it's got one variable, which is that RS, that missing value. I can solve for it. So I'm going to take away 9 from both sides, and I can get RS equals, my brain's breaking right here, that would be 13. And the last thing I want to do, and I know this is going to be a nitpicky thing, and our final answer, RS equals 13, I would not give myself full credit if I left it this way. It will be 13 units. We want to be absolutely perfect with our notation. If we can be perfect with our notation, meaning RS, no segment bar, the distance from R to S equals 13. 13 what? 13 units. If they gave us centimeters, awesome. If they didn't, we're going to put units down. And then some of you might be wondering, hey, why did you use the equation 22 minus 9 equals 13? It's because if we get in a habit of setting up the equation we're given from the segment addition postulate, we're going to be better when it comes to maybe more involved ones, like this next one. It says find JK. So JK is 2x, we have KL is 4x plus 3, and then the whole thing is 33. What do we know? We know the segment addition postulate. We are assuming this to be true. That's what a postulate is. JK plus KL equals, you know what, I might do this in different colors. So JK plus KL equals JL. And now I'm going to go in and put what I know about each one. I know JK is 2x. I know that KL is equal to 4x plus 3. And I know that my whole JL is 33. And what I know about the segment addition postulate, if I were to take the two parts, if I were to add them together, they would have to be equal to the whole. So for this one right here, we need to find JK, but in order to do that, I need to have one unknown solved for first. That one unknown value, you probably guessed, is x. So if I can solve for x, which thank goodness we took algebra, pre-algebra, middle school math, we will know how to solve this equation. I got like terms, so I got 6x. How I did that was 2x plus 4x. I got 6x plus 3 equals 33. I'm going to use subtraction property, so take away 3 from both sides. I'm going to have to move over here. I'm actually going to put this over here. We've got 6x, these 3's cancel out, equals 30, divide 6 by both sides, and x equals 5. Is that our final answer? No, it's not our final answer. We are trying to find JK. So what we would do is we would again go back and say JK is equal to, and over here it says 2x. If I sub that in, it'd be 2 times 5. So my final answer is JK equals 10. And do not leave your final answer like that. It is equal to 10 units. And another reminder that we read this as the distance from J to K is 10 units. Awesome. So we just have two more things left, and this is going to talk a little bit more about the idea of the difference of notation. So it says if I see this equal here, this equal sign means equal to. The distance from A to B is equal to the distance from C to D. If we are talking about values, if we are talking about a distance, if we can measure it, if it's talking about measurement, we will use a quality, the equal sign. Because AB could be 5 centimeters long. So we could say AB is 5 centimeters long, that is equal to CD because it is also 5 centimeters long. And now we're going to introduce something new, this word congruent. Maybe it's new, maybe it's not. I'm going to assume that it's not. It is new. They are line segments that have the same length, but really the key here, I want you to think same. Congruent means same. I am not dealing with measurement at all. I am saying that these two segments or angles or whatever we are saying is congruent, in this case it's segments, we are saying they are the absolute same. They are copies of each other. So when I see this, which let me draw it for you, I can show you an example. When you see congruent, it's an equal sign with a little squiggly above it. That means is congruent. So how I would read this second one here is I would say that segment AB, notice I'm saying segment AB because of the bar, is congruent to segment CD. Compare that to the first one where the distance from AB is equal to the distance CD. We will begin to talk about this and the subtle differences. Why do we have equals and congruent? They mean two separate things. Equals is talking about values. That's why in algebra you see it a lot. You're talking about numerical values. Congruency is talking about, are they the same? I like to think, are they copies of each other? Are these segments the exact same? Can I map one onto another? And just to show here, graph the points. And we're going to our final example. This will be the last one here. Graph the points x, y, w, and z in the coordinate plane. Our segment xy and segment wz congruent. So let's find out. X is -2, -5. So -2, 1, 2, 3, 4. Oh, you know what? I'm gonna have to get a smaller, probably marking here. Let's go a little bit deeper. 1, 2, 1, 2, 3, 4, 5. Oh, I went the wrong way. It's supposed to be -5. 1, 2, 3, 4, 5. And just even when we're on the coordinate plane, we'll always give our point a name. Y is -2, 3. 1, 2, 3. We got Y, and there is our segment. Change colors. Let's do that. I like that pink though. So W is -4, 3. 1, 2, 3, 4. 1, 2, 3. So we got W. And Z is 4, 3. 1, 2, 3, 4. 1, 2, 3. And got Z. Connect those up. So I'm going to right over here to the side, we have WZ, or I should say, the distance from W to Z. And then we're also going to take a look at the distance. Oops, that is not what I wanted. Distance. Oh, my goodness, we're falling apart here at the end. I think I was on that one. XY. Okay, so with this, because they're vertical, because they're horizontal, we'll just be able to count the distance here. So for XY, I'm getting 1, 2, let me get that 1, 2, 3, 4, 5, 6, 7, 8. So I'm getting 8 units. And for WZ, I'm getting 1, 2, 3, 4, 5, 6, 7, 8. 8 units as well. The question was, are XY and XZ congruent? Are they congruent segments? Let's go look at our definition. Our definition said line segments that have the same length. So let's go check. Here is the distance of these segments. The distance from X to Y is 8 units. W to Z is 8 units. Are these the same? Oop. Let's get a different color. Are these the same? They are the same. So because they are the same, we can have our final answer to say that these two segments are congruent. So our final answer, segment XY is congruent to segment WZ. All right, so a little bit of a longer video of this one. I apologize for that. Thank you for sticking in there. So again, we're going to come back together. This ends our section 1.2 notes. Thanks for watching. I'll see you guys next time.